let's look at one that's a little bit more interesting. You have something like 16a squared minus 25b squared. Well, 16 is a perfect square, and I've got this a squared, two terms subtracted. 25 is also a perfect square, and so is the b. I don't see a common factor. It's not a trinomial, and I'm not going to factor this by grouping because I would need to have four terms written out. So let me see how I could rewrite this as squares. If I wrote this as a 4a in parentheses squared, I would have my 16a squared written out as one little unit that's squared. And the 25b squared is really 5b squared. Now this fits my pattern. This would be my x, and this would be my y. So I'm going to write x plus y, x minus y. In this case, that's going to be 4a plus 5b times 4a minus 5b. And that's my answer. Let's do another example. Let's factor 121 r squared minus x plus 1 squared. Nothing in common. Not going to factor by grouping because I don't have four terms added up. That's my hot tip there. It's not a trinomial, but I see two things added up. I see the power 2 running around, and I happen to recognize 121 as 11 squared. So let me rewrite this as 11r squared minus x plus 1 squared. Now, the 11r is my x in the pattern. This entire x plus 1 is my y in the pattern. So I'm just going to haul around the entire binomial in parentheses. We're going to factor that then. Let me just write out to remind, x plus y times x minus y. Well, that then will be an 11r plus x plus 1 times 11r minus x plus 1. Looks a little fancier, but it's the same pattern. And that I can simplify a little bit by writing 11r plus x plus 1. There's no need to keep those extra parentheses. Times 11r, and just using the distributive property with that negative sign, which is really a negative 1, minus x minus 1. And that would be my answer for that problem. Now, again, the key to all of this is to recognize squares. So you're going to have to know 1 squared is 1. That one's usually pretty straightforward. 2 squared is 4. 3 squared is 9, and so on, at least up through 100, which is 10 squared. A caution: x squared plus y squared is prime. Don't try to use this pattern when you have a sum of squares. It won't work. Now, I told you I was going to mention the other patterns. This is just so that you have them for reference to look up in your book. If you like using patterns. First of all, you have your perfect square trinomials, and that's just undoing squares. When you have something like x squared plus 2xy plus y squared, that came out of x plus y squared, and then you had x squared minus 2xy plus y squared. reversing our multiplication again, that's going to be x minus y squared. You have also the sum and difference of two cubes, and again, in this case, if you're going to use the pattern, you have to recognize perfect cubes. It's not a pattern that you would ordinarily memorize. You can always use the product sum table when you see these, so you don't have to know these by heart. Sum and difference of cubes you would typically look up the patterns for, unless you're using them a whole lot and they kind of sink into your hand. X minus y times x squared plus xy plus y squared for the difference. And you can't break it down any further than that. This is the factored form. And then if they're added up, you're just looking at a sign change. You'll have x plus y times x squared minus xy plus y squared. And that's the end of this segment.